In today's video we're going to be talking about the concept of the determinant, and specifically we're going to be talking about the value of the determinant being equal to the area of a parallelogram. Specifically we're going to be discussing 2 by 2 matrices, and for example we have a matrix here A with real values A, B, C, and D, and with the 2 by 2 we know that the definition of the determinant of this matrix is the product of the diagonal terms, so that would be A times D, and then we have minus the product of the off diagonal terms, so that would be B times C. And we're going to show, as I mentioned, that that is equal to the area of a parallelogram that we're going to define very shortly here. So which particular parallelogram are we talking about? Well, it's the parallelogram spanned by the column vectors of the matrix. So we're going to go ahead and label these. We're going to call this particular column vector U, and we're going to call this column vector V. And we're going to come back over here, and you can see I've already drawn these ahead of time. So this one U is going to be equal to a column vector AB, and then we're going to let V be equal to CD. And like I said, we're going to talk about a parallelogram, and the specific parallelogram is going to be this particular one. We're going to take U and slide it up here, and then we're going to take V and slide it over here to define a particular parallelogram like that, that's spanned by the column vectors. And we're going to show that the area of this parallelogram is equal to the value of the determinant. So what is the area of a parallelogram? We're going to come over here and say the value of the determinant is equal to the area, which is our hypothesis. And what is the area of a parallelogram? The area of a parallelogram is, of course, base times height. Okay, so we're going to come back over here and we're going to label up the base, and we're going to call this the base B, and it's just going to be the length of this vector. So the base B is going to be equal to the magnitude of the vector U, which should be fairly obvious. And we're going to denote the magnitude or norm of the vector with these double bars here. The height is a different story. It's not a little bit trickier to get a hold of, but it's if we drop a perpendicular here, and this is a perpendicular to B, we're going to call this magnitude H, which is the height of the parallelogram. And the height is dependent on V, but it's also dependent on this angle here. So we're going to go ahead and label this angle theta. Okay, and then obviously from our trigonometry class we know that this value here is equal to the magnitude of V times the sine of theta. So we're going to go ahead and write that down over here. So H is going to be equal to the magnitude of V times the sine of theta. So we're going to go ahead and substitute those two values in here. So we're going to say equals the magnitude of U times the magnitude of V times the sine of theta. Okay, well, this is an interesting form, and it looks like something we might be familiar with. It's looks like kind of like a cross product, and it almost looks like a dot product, except for the fact that there's a sign here rather than a cosine. And our plan is going to be to transform this expression to be exactly equal to a dot product. So we're going to have to change a few things around. And the first thing I want you to notice is that we have a normal here to the base, drawn by this green line or green vector. And because it's a normal, we can look at this angle here, and we know what this angle is, and we're going to label that phi. And we know that theta plus phi is equal to 90 degrees, or you can use pi over 2 if you prefer radians. And then we can solve for theta. So theta equals 90 minus phi. And then we can substitute in here. So we're going to go ahead and write this equation again with that substitution in place. Magnitude of u, and then we get the magnitude of v, and then we get the sine, and again theta equals 90 minus phi, so we're going to put that in here, 90 minus phi, and then we're going to draw on a property that we learned in trigonometry. Maybe not remember it, but and that is that the sine of 90 minus an angle, and we'll just use a different symbol, alpha, is equal to the cosine of that angle. Okay, so we're going to do that substitution here, and that should be obvious because the sine of theta kind of projects this vector down onto this normal, and then the cosine of phi likewise projects this vector down onto the normal. So they're the same thing. Complementary angles behave that way. So we're going to go ahead and write our equation again, and this time we're going to get a cosine involved. So we're getting a little bit closer to where we want to go. So then we get cosine of phi. Okay, so now we have something that looks a little bit more like a dot product, except for we have u over here and we have v over here times the cosine, not of the angle between them, but of this angle on the outside of them. So how can we transform this where we have two magnitudes and we have an angle, a cosine of the angle between them? And what we're going to do is we're going to look at this particular vector here, which is perpendicular to u, and we're going to define this vector as being a rotation. We're just going to draw the rotation like this, and that rotation is 90 degrees. So we're going to take u, we're going to rotate it 90 degrees, and we're going to relabel it as w. So we're going to let w equal, and we're going to draw our rotation operator here as r of 90. We're going to draw a little counterclockwise rotation symbol there. And then that's going to be of u. So operating on u, a rotation of u by 90 degrees gives us w. And then we're going to go ahead and express the rotation matrix, or express the rotation as a matrix, and that's going to be equal to the matrix 0, minus 1, 1, 0. And you can, if you're familiar with rotation matrices, you can verify that that indeed is a rotation matrix by 90 degrees in the counterclockwise direction. And then that's multiplied by u, and of course u is a and b. Okay, and then we can go ahead and do the multiplication, and we'll make the colors in the color of w. So we multiply this, the column of this, by the first row when we get a negative b, and then we multiply this column by the second row and we get a. Okay, so it kind of flips the terms around and negates b. And if we want to look at this diagram, we can easily see that if this is a and b and the x-coordinate is a, when we rotate 90 degrees, the x-coordinate becomes the y-coordinate of the new vector, and that's what we see going on here. X goes to y. Then what happens to the y value? So we have here, we have b, and that of course comes from here. What happens to b? It comes here, but it becomes a negative, so we have negative b. So the value that was the y value becomes negative x, and that's what we see here. So what are the magnitudes of these vectors? Well, let's look at u first. So the magnitude of u, of course, is, by the Pythagorean theorem, it's going to be equal to the square root of a plus b squared squared. Okay, and what is the magnitude of w? The magnitude of w is going to be equal to the square root, and we get, if we want to be really thorough about it, it's minus b quantity squared plus a squared. And of course the negative sign goes away with the b. We switch terms around, and what we do is we get a squared plus b squared. So what we have is we have that the magnitude of w is equal to the magnitude of u. So we can go ahead and substitute that in over here in our equation here, and we get, substituting for u the magnitude of w, and then we still have the magnitude of v, and then we have the cosine of phi. So now we have our desired form. We have a vector w, we have a vector v, and we have the cosine of the angle between them. So we can re-express this as a dot product. So that equals to just w dot v. And then we'll write this as an inner product in matrix form. So in matrix form, that would be equivalent to w transpose times v. And then if we write that out here, that's going to be equal to, so w transpose, let's write that in green, w transpose, so w is minus ba, so we have minus b times a, or minus b and a, and we'll write that in blue. And then we get, of course, v is c d, and then if we multiply this matrix out, we'll just write it in yellow. So we have minus b times c, so minus b times c, and then we have a times d plus a times d. And if we swap these terms around, we get the familiar a d minus b c. And I'll put that in a box because that is the value of the determinant that we have from the standard definition for a 2x2 matrix. So we have demonstrated that the value of the determinant for a 2x2 matrix is equal to the area of a parallelogram spanned by the column vectors of the matrix. The same will work for the row vector because the transpose of a matrix has the same determinant. And thank you for watching my video.